best of my knowledge, we do not have any further. I'm not supposed to have any further missing lectures until the end of the semester, and of course, if needed, it will compensate for the 2 lectures that we've missed. Hopefully, more students will come. We have a fairly technical, mathematical, quite interesting actually, I think, but a little confusing lecture today. But before that, let's do a recap. Because last time, which was before Yom Ha'atzmaut, we completed the discussion on the principle of equivalence. And we showed that the basic philosophical idea was that every place that there is a gravity, we can always replace that with an acceleration which has nothing to do with gravity, which comes from the Otmoshes experiment. And from that we derive the equation, and then from that we derive the equation of motion of a free particle. Equation of motion of a free particle in arbitrary gravitational field. And here comes a crucial semantic, you can say, difference between GR and everything else you learned so far. In GR, gravity is not a force. So when we say free particle, then it's free from other forces, not from gravity. And we show that it is du lambda over d tau is minus the affine connection u mu u mu. And the affine connection gamma lambda mu nu was defined as the x lambda over d psi alpha is squared psi alpha over d x mu d x nu. And we show that this affine connection is directly related to the metric tensor by gamma sigma lambda mu is 1/2 g nu sigma dg mu nu over dx lambda plus dg lambda mu over dx mu minus dg mu lambda over dx. So if we know the metric, and then we can take its derivative with respect to different coordinates, and from that we can calculate the affine connection, which in turn tells us what would be the acceleration. Essentially, that plays the role of the gravitational force, but this is an interpretation already. What we did here so far was totally mathematical. And then we showed that we obtained the geodesic equation from the, this is the geodesic equation. And we show that it is obtained from the variational principle. Meaning it is the shortest path between 2 points. In a Lagrangian manner. This is namely the time that minimizes the path that minimizes the proper time between 2 points. Okay. So that's why so far this is a completely mathematical description. That's, I gave you the example of airplanes that are forced to move in the Earth's atmosphere between 2 points, and so they move along geodesics, because this is the shortest path. Again, the main interest is, of course, to minimize the fuel, the money, of course, the flight time as well. So they take you through the shortest path, which is not always looks like it if you're trying to take the map of the Earth, to map the Earth surface, which is a sphere, into a 2-dimensional sphere, because the Earth's space is not a Euclidean space. that's why it sometimes look, especially when you go for long distance flights from here to North America, it seems that they go in a circle closer to the North Pole than you think they are, but in reality this is simply the shortest path. And your homework is supposed to show it. And then the last thing we did was to look at the Newtonian limit. So we took this geodesic equation and we looked what happened when slowly moving particle, that's 1, 2, weak gravitational field, and 3, static field. Static gravitational field. Static meaning not changing in time. And we show that in this case, if we identify G00 is minus 1 plus 2 phi over c squared, where phi is the gravitational potential, then we end up with the Newtonian force. So geodesic equation in the Newtonian limit gives us the Newtonian force. So we know that we're doing something right, because although this theory was developed more than 200 years after Einstein's, after Newton introduces gravity, the fact that we retrieve back the Newtonian gravitational force is a very good sign, of course. It would be very embarrassing to build a theory which would be completely contradictory to Newton. Which obviously has been tested multiple times, but enormous number of times, multiple, but always in these limits. Questions before we move on?
Usually then we are solving some problems. We don't use really the definition, the phi connection, but rather this connection.
Depends on the problem it has. It's often more convenient to use that.
Yes, this one.
Because often it's much easier when you have a problem to set the metric, or it's given to you, or you can think of what is the metric, and then it's much more straightforward to use that. But these are equivalent, basically. So it's just a matter of convenience. Right? Or you're right that practically this is going to be a much more useful formula than this one. But at the end of the day, there's. Okay, so today, most of the time, I'm going to do a lot of math. I'll tell you all the outcomes so that you won't get confused. But let's do one step at a time. So today we start a new subject, which is called vectors and tensors in closed spacetime. Remember that that we had two problems that we want to solve in the realm of geometry. Okay. The first one was how to describe the motion of a test particle in the presence of a gravitational field. This we solved. The answer is the geodesic equation. Great. The second problem was how do the existence of mass or energy is equal to mc squared acts to curve space-time to make it non-Euclidean. The answer to that is much more complicated. That's called Einstein's field equation. And basically what we're going to do in the next few weeks of the semester is to derive eventually Einstein's field equation. But before that, we need to understand what do we mean exactly by curved space-times. We have to be a bit more careful here. So I just write it down. How does the presence of gravitational field curves space-time? The answer is Einstein's field equation. But yeah, there is a mathematical gap which we need to cross here, and that is, we're doing physics, so we need to write down physical equations. And equations in physics we're going to write in terms of vectors and tensors. So the question is, how do we write vectors and tensors in curved space-time, or in curved spaces in general? Okay. And to get slightly deeper into what I mean by that, we're going to encounter a next principle, which is called the principle of general covariance. This course is full of principles. So the problem at hand is to understand how the laws of physics, general, not just gravity, any laws of physics, adapt to a curvature of space-time. Okay? Electricity, strong force, weak force. How do the laws of physics adapt to the curved space-time? And the answer is given by this principle, which is in a sense quite similar to what we did with the equivalence principle. So we do the following. Number one is consider an equation that describes a law of physics without gravity, namely in a flat space. So we wrote down something. Typically, how do we write physical equations? So partial. What?
Differential.
Yeah, it's always differential equation. It's a partial differential equation. It's a typical equation of physics. Now, I'm arguing, according to this, according to the equivalence principle, this equation will hold in the presence of gravity, if it is generally covariant. Meaning, it preserves its form. Under general coordinate transformation. Wait, take a second to think of what I just wrote down here. If I have an equation that I know is right without gravity, and when I put gravity, the equation looks the same, I know it's correct also. This is called the principle of general covariance. And the proof is pretty straightforward. Because this follows directly from the equivalence principle, right? Just see that. So, suppose we are proof, right? Let's say that we're in an arbitrary gravitational field. Consider an arbitrary gravitational field. Arbitrary curved space-time. And we have some equation that fulfills these two conditions. And an equation fulfills the above. From this condition, it says that if it is true in one frame, it's true in any frame. Right? So from 2, if true in one coordinate system, it is true in all. Now, then we have the equivalence principle. Says that wherever we are, we can always find a coordinate system in which there is no gravity. Right? In that point, in the point in question, we can always find a coordinate system freely falling. And then for 1, the equation works in that frame. Right? The equation holds in that frame. Right? So it describes some law of physics. If you think of it some more, home, what it really tells us is that the laws of physics are independent on the chosen coordinate system. This is what it really tells us, which makes perfect sense. At the end of the day, coordinate system is something which we put for ourselves, and the physics doesn't know about it. It's our selection. It would be very embarrassing if the laws of physics would depend on which coordinate system we choose to work with. There's something quite deep in here. Because of this principle, it explains why we spend so much time working with vectors and tensors. Why is that? Because we can easily transform them from one coordinate to another. So we know to transform the equation from one coordinate to another and see right away if it holds or not, if it preserves its form or not. Okay. So basically, equations that are made with vectors and tensors are easily transformed and can be easily put in this general covariance form. Means we can use them to describe physics. Okay. Essentially, what we're going to do from here on in the next few lectures would be to generalize the notion of vectors and tensors that we introduced in special relativity to any arbitrary curved spacetime. Okay, so that we could write down equations with vectors and tensors in any arbitrary curved spacetime. Okay, you all with me? So the next thing I'm going to do is to start by generalizing the definitions of vectors and tensors into curved space.
Maybe you can give an example of an equation that fulfills the conditions and one that doesn't.
You'll see many. Generalization of the definitions of vectors and tensors curved spacetime. I say spacetime, but what we're going to do is completely mathematical, so spaces. And what I'm going to do for the rest of today is going to be summarized in one sentence, which is, I see that we just lost 1/3 of the class, which is vectors are really directional derivatives. And class right here. What is a directional derivative? Possibly you don't know because you did not encounter this term before. What is a directional derivative?
You can write it as a scalar product of gradient and some vector.
It's much simpler. Right? It is a generalization of the idea of a partial derivative. Right? What is a partial derivative? You keep all the coordinates fixed but one. Right? You have coordinates. Mm-hmm. There is a full derivative, right? There is a partial derivative. So if you have a function that depends on some coordinates, basically you keep all of them except one fixed, and this one you're looking at how this function changes when this coordinate changes. So directional derivative is you just select one direction, not necessarily along the coordinate, right? And you're looking how this function changes along this direction. And this we call a vector. one step at a time. What is the problem? When we describe, when we introduce vectors, I told you that there is one key thing, and that is that vectors belong to a point. Right? That was a key thing which I emphasized and I stressed it. Right? Vectors belong to a tangent space at a given point. Vectors belong to a tangent space at a given point. That is true. I wasn't lying. That's okay. That's true. But then there is a price we pay. We lost the sense of direction. We can no longer say that the vector points in a direction. Like normally we think, okay, vector points in x direction, in the north direction, whichever. No. Vectors belong to a point, there's no direction. But we need this direction. So now we're going to get back the idea of direction. Now, let's do it slowly. I'm taking the shortest path I can, namely I'm just leaving only the math that I think is essential. I'm not going to do. I put an appendix with all the math that is needed, but to be precise, but here I'm just giving you the intuition and the minimum math that is needed to. You see that I'm not cheating. So the first thing we need to define, even vaguely, is this concept of a manifold. Now there is an entire definition which will take us about an hour to give it. So I will reserve it to an appendix. Maybe it may appear in tutorial. Right. So what I said, which is not a mathematical, exact mathematical definition, but it's good enough. It's a manifold. It's an n-dimensional S space that near each of its points resembles an n-dimensional Euclidean space. Means locally around each point it looks Euclidean, but globally it is not. Okay? So locally around each point it looks Euclidean, but globally it is not. Some basic examples, right? Let's think of a sphere. Right, surface of the Earth. If I look locally near each point, if I go close enough, it resembles Euclidean space. But of course, globally it is not. Another example is torus. Torus is also locally around the torus. It always looks Euclidean. You have a double bagel. And by the way, it's called genus C. Genus 0. This is a genus 1. Let's call it a Riemann surface. That's the correct notation. What is not a manifold? Like something like a porcupine, right? If I have that spike, that's not a manifold. Right? It's physics, it's not math, so I'm thinking of simply well-behaved spaces. And again, for me, well-behaved is, every point, doesn't matter which one, every point, if I look around it close enough, it resembles Euclid. Okay? That's a minute. I don't think you've seen that before. You've all taken calculus in field 1, 2, 3. Okay, so this is not a manifold. Now, I want to define a vector in this case. Now, I already gave you the answer. Vectors are directional derivatives. I'm going to do it slowly, so you see we need a little bit of an imagination. Because the tricky point is that I want to define vectors, but only using things that are intrinsic to a manifold, not something which is external to the manifold. I'm inside the manifold. I can think of an ant. I'm an ant. I'm forced to live on that manifold, and I want to define some things intrinsic to it. How am I going to do it? So it's okay, I'm going to erase it. So again, there is a mathematical definition of a manifold which requires certain stages to go through. Eventually it will look exactly like that.
Locally means infinitesimal?
Yes, it can be infinitesimal. Depends on the manifold. Could be, when I say resembles Euclidean, right? I select a point. How close do I need to be to the point? That depends on how much deviation I allow myself from Euclidean. It's fair enough. But there is always close enough. And here I can look at this class as being flat. It's not part of the surface, which is not Euclidean, but it's good enough for me. So, vectors and curved spaces. Another thing, just we think of, vectors are basically structures that we put on a manifold. So we don't need vectors to define a manifold. Like, vector is something external which you add to the manifold as an external structure. So you have a manifold. I'm drawing it a large manifold by purpose, and I'm choosing a point P on that manifold. And manifold I call M. So the goal is to construct a tangent space at V, TP, using only things that are intrinsic to the manifold. We're going to have to use a little bit of imagination and a few tricky points, but it's actually quite fun. So, what did we say is a tangent space? just lie in the tangent space, TP. Vectors. TP vector. Dual space is called. But how did we set vectors? What were they?
Tangent to the manifold.
What? There were tangent vectors to curves. What can we do in a manifold? Not too many things, really. What can I do? I can draw a curve on the manifold. Just think of it like I'm walking on a tree. So I can draw a curve along the manifold. I'm walking, hiking. And now I can specify the curve by some parameter. I call it lambda. That's legal. I didn't pick the manifold. Okay. Now I can think of this curve as so what? Actually is a mapping from R to M. So let's call this curve. I call this curve gamma. And the curve gamma is a mapping from M to R. What does it mean, mapping from M to R? What's at the mapping? The parameter lambda, right? So I tell you, right? I'm now here at this point here, right? This is a point in M, on the manifold M, right? But now I specify this is for me lambda equal to 0. This is for me lambda equal to 1. This is 1 to 2, lambda equal to 3, 4, 5. Okay. So I can think of this map of this curve as a mapping, right? For every point in M along this curve, I give it a number, lambda. Okay. Or sorry, vice versa. R to M. Yeah, if it's parameters, could be it's from R to M. R, and from the same reason, right? If I tell you, I call you on the phone, I tell you, okay, I reach point number 3. I mean, I'm here. You know where I am on the manifold. So obviously the point P, as I draw it, is one of these points on this curve. Fine. So first attempt might be to try and simply define TP as all the curves that go through P. Another curve, another curve, another curve. Right? Thing is, I still didn't say what does it mean a tangent vector to a curve. Just saying there is a curve. I didn't say anything more than that. So this is the first attempt. Now we have a second attempt. Second attempt would be what? Would be to say, okay, we know that the M is a legitimate manifold. Right? What does it mean? It means that near every point, it's Euclidean, right? If it's Euclidean, I can draw a coordinate system. Right? So I can set a set of coordinate system, x mu, at the vicinity of the point P. So I have a coordinate system. X mu. X P. This is legal because M is a manifold. So once I set this coordinate system, and I look now again at the curve. Now what does a curve tell me? after setting a coordinate system, set a coordinate system in the vicinity of P. I look again at this curve now. Now what does this curve, how can I look at this curve now?
Direction of the vector.
What?
Direction.
Not yet.
It's mapping also.
What?
It's mapping.
It's a mapping.
But
That's right. That's the correct way to think. It's a
from
mapping.
R to Rn.
Yes, very good. It defines an element, so a curve defines an element in Rn. Right, this curve now, the curve defines an element in Rn. Right? N is the dimension, so the number of coordinates. Which is what? That's exactly the dx mu over d lambda. Right? How x mu changes when lambda changes. Of course, all it's point P. If I happen to have a curve that goes exactly along the one of the coordinates, goes along one of the coordinates, what will be these end numbers? Dx mu over d x mu over d lambda of that specific curve that I have there via the point P.
It will be a vector.
It will be dx1 over d lambda and then 0, 0, 0.
Yeah.
This specific one. Because only the first one changes. It's lambda.
Only one non-zero
Yes.
component.
That's fine. That's quite good. We're nearly there. We still have one problem. Well, this already looks like a vector. We still have one problem, which is that this is dependent on the coordinates. We don't want that, right? Because we can set any coordinates that we want. So we want to have something which is more general than that. Okay? So we want to do something which is independent on coordinates.
But components of a vector can depend on coordinate system. It's fine, but the length of the vector not. What's the problem?
Oh. I did not specify. I want to do something which is completely general. Remember, right now I want to I want to define the tangent space in the point P in order to define the vectors. Right? What we're doing right now is redefining the concept of a vector, which I already gave you the answer.
What is the motivation for it? What is basically different? In any other physics, it's okay, but where the coordinates are dependent.
No. Any other physics, you never encounter to do physics in a curved space.
No, that's correct.
You always did physics in Euclidean spaces. The space was well defined. Now I'm saying what happens when the space is curved.
But what is the problem?
The problem is that the vectors are defined only at the point. We're going to have to get back to the idea of derivatives of direction, because we need to have derivatives between one point to another. How do we get that when the vectors are how do you compare a vector at point here? This is t q. This t I don't know s, and this would be ts. How do you compare these vectors? Right. So what I'm doing, it's a mathematical game. I'm showing to you that you see that it's not that trivial. It's not that difficult at the end, right? It's a mathematical trick. We're nearly there. But just to give you the feeling that it's absolutely not something which is trivial. Okay? To set a vector to set vectors in curved space. curved spaces. Okay, we said we are nearly there. The only problem we have is that we want something which is coordinate independent. So the way to do it is to think of what is this coordinate system. So we set a coordinate system. So the coordinate system again, you can think of it as a what? It's a mapping. It's a mapping from M to Rn. Map from M to Rn. Right? Every point in M gets a set of n numbers. It's this coordinate system. Right? And any curve with it's a function at p, right? The x mu over the lambda. So to generalize this notion, what we do, we look at f as a space of all smooth functions on M. On M. We say that it's C infinity, which means that it's infinitely many times derivatives. F from M to R. And then each curve is defines an operator on the space which is exactly the directional derivative. Which maps f to df over d lambda. Of course, at
by term space, do you mean that it's a vector space?
the function space. It's the space of all smooth functions.
Yeah, but it's vector space. I can add two functions.
Yeah,
It's linear and all of this.
You can, yes, but you can think of it as generalizing of all the coordinates, basically, or any function that you have. Yeah, you just have to think of it. There's nothing more that I can say right now. Except that, what you hear, right? And the second thing is that directional derivative is simply generalization of the idea of partial derivative. So directional derivative is a generalization of partial derivatives. And now we can make the claim. So the argument is that the tangent space TP is identified, can be identified with a space along curves through P. It's confusing, but at the end of the day, you have to think a little bit about that. You end up that there's nothing much you can add to that, or nothing much you can do. So to prove this claim, we need to show two things. One, this is a vector space. And two, that this is the vector space we want.
What exactly do you mean by second?
This is the vector space that we can associate with vectors.
I mean that it's not a function vector space. Not
Yeah, I mean that it's the same dimension. It has the same direction of vectors that we'd expect the vectors to have. Basically, that we can identify a vector with directional derivative, which we're nearly there because we did half of the things by just showing this curve that it was there.
But why now if it's not dependent on the
Because it is defined in a coordinate independent way. That was the last part that I did here.
Okay.
Saying instead of, I could have stopped at the second point saying, okay, I draw coordinates and I have a directional derivative along these coordinates, right? But I said I don't want that. I want something which is coordinate independent. So that was the last part of the generalization I had, was saying, rather than looking at a specific coordinate, which I can think of them as a mapping from M to R, let's look at all the general functions of M to R. Okay, that was the last bit here. I look at the general functions from M to R, all smooth functions, that's called C infinity, from M to R, and then I look at all the curves that can go through there, and I'm saying each curve specifies a directional derivative, like that, over all functions, which is completely general. So that was the missing part. So one is to show that this is a vector space. What does it mean, a vector space? That it obeys everything from vector space. So if we have two vectors, operators, so consider two operators. Say d over d lambda, d over d eta. Two elements in this space. And both representing two derivatives along two curves that go through P. So obviously we can add them, we can multiply them by real numbers. So we can obtain the operator by A d over d lambda plus b d over d eta is a new operator. So no problem. But is this a derivative operator? The answer is obviously yes, because when we work on function, it has to work in a linear way, and for that we have the Leibniz rule. So I use the product rule. Is this the operator belong? Is the new operator? Does the new operator belong to the vector space? Well, we can simply use the Leibniz rule. operator A d over d lambda plus b d over d eta operated on G. Two functions that belong to F. Then obviously this is A F dg d lambda plus A G df d lambda plus V F dg d eta plus V G df d eta. So A df d lambda plus V df d eta G plus A G d lambda plus B G d eta F, using the same standard rules that you're familiar with. Those F and G belong to F. Space of all smooth functions. So essentially this is just to show that this is a derivative operator. Which indeed that essentially this is a vector space. And is this vector space a space we can identify with TP? The answer is obviously yes. So can we identify this with TP? The answer is yes. I have to erase that. Can we identify this space with TP? So yes. Simplest way again. Well, look at the basis. Again, look at the point P. I'm drawing some coordinates. Point P. Let's call this x1, x2. So this would be d over dx1, d1, d2. Good. So, if we have a look at so consider a coordinate chart, a coordinate basic. Consider a okay. The technical word is a coordinate chart. When they get into this definition, essentially, Kללית coordinate system. I should just mention it since I already said it. Technically, what is the coordinate chart? I said in the vicinity of P, I can always put the coordinates because it's Euclidean, very close enough. Coordinate chart would be simply to choose a open set U, and coordinate chart would be a function phi from U to R. So I can always find a set of open points around P and then a function from U to Rn. This is called coordinate chart. Essentially, this is what coordinates do, if you think of it these coordinates. Going back to mapping from a point on the manifold to Rn. That's why it's called a chart. It's an open set field. Okay? And I don't want to get into that because I guess you're already confused enough. So there is an obvious set of n directional derivatives on P. Which is already noted here. Okay. V mu at P. Again, which defines the directional derivative along curves that happen to be going along these coordinates that we chosen arbitrarily. Now the claim is that this set of partial derivative form a basis for the vector space. Okay, so claim that the set of d mu form the basis d mu at P form a basis to the tangent space TP. How do we show this a basis? I showed any vector can be spanned with d mu, and that obviously this is simply the components of any tangent vector. But this is the component. These are the components. But these are the components of any tangent vector. So again, if we have a curve gamma, consider a curve gamma from M to R. Sorry, from R to M. This is my curve gamma. R to M. Any function f from M to R. So d over d gamma, d over d lambda, sorry, of the function f. You can write it as a what? Again, so I'm specifying a function here, right, which for every point in M gives me some number. Think of it as a height of a mountain, if you want. I specify a curve, right, and then d over the lambda of f is a what? Is a lim of epsilon goes to 0 of f of x mu at the point lambda plus epsilon minus f of x mu of lambda over epsilon. Yeah. Which is what? This is just dx mu over d lambda the f over dx. Now, f is arbitrary function. I didn't say what it is. Which means what? that d over d lambda I can write as dx mu over d lambda times d mu. Which is exactly what I wanted. Argue the d mu from a basis. So I can look at dx mu over d lambda as the components of the vector d over d lambda in that basis, x mu. Right?
Could you explain again why is the derivative of f with respect to lambda equals to the x
This
mu
is
of
the definition.
lambda?
That's exactly the
No,
definition
no.
of a derivative.
I mean the next. Yes.
Just put it in here. Take f at x, the point x mu of lambda plus epsilon minus f at x mu of lambda. That's it. Go back to basic calculus. Let's say it right away. But this is what? Of course, is the tangent vector to the curve, yeah. This tangent vector to yeah. Essentially, I told you it's going to be very mathematical today. Hopefully, it's fun. Essentially, all we did was to replace, in special relativity, we spoke of basis vectors, E, U, right? As basis vectors. What did we do? We just replaced them with the mu. That's all. This is known as the coordinate basis, right? Because we selected a set of coordinates and then we just decided that the basis would be along these coordinates. Okay. This is known as the coordinate basis. The new coordinate basis. I should say that this is very handy, but not always. In some problems, you actually don't want to work with coordinate basis for various reasons. They don't have to be orthonormal. Various reasons they don't have to be normalized. Many things. Yeah. The coordinate bases, they don't have to be normalized to unity and they don't have to be orthogonal to each other. I selected my coordinates. It's my choice. Okay? Now we worked very hard and very confusing to tell you something which I told you the first 5 minutes of the lecture. Vectors are directional derivatives. The advantage of doing that, all the transformation laws become now very simple. Actually, very much straightforward. So.
But still the component depends on x mu.
Sorry?
Still the component depends on x mu.
Yes.
That's a problem.
That's not a problem. Because this is the components of a vector in that particular basis. If I'm going to a different basis, I will change the components. If I write a vector, just think of a vector, 2D simple Euclidean space, which you write the vector in Cartesian coordinates, x and y, versus polar coordinates, r and theta. The components of the vector will be depending on whether you're working in x and y or r and theta. There's no problem with it. The vector itself does not change. It's the components of the vector that change when you're changing coordinates basis. Okay. Which is exactly what I want to say right now. Let's say that I switch now coordinate basis, right? So if I'm switching from in a new coordinate basis, x mu prime, how do I specify the basis vectors in the new coordinate basis? I'm asking about the basis vectors, v mu. V mu prime.
במונחי הבסיס הקודם?
Yeah.
So dx mu prime over d mu.
Opposite.
נכון.
V mu prime is d over dx mu prime. So I have a dx mu over dx mu prime, d.
But it's just Jacobian matrix, right?
Exactly. Just a chain rule. Pretty much very straightforward. There's nothing else right here. So if you want the transformation of the vector components, so transformation of the vector component or the vector v, right? So it's v mu, d mu, right? This is the basis. What happens to the vector when I'm changing the basis? Nothing. So I just need to take the inverse of this matrix, which is what? Just the x mu prime over the x mu. Write down that v mu prime is the x mu prime over dx mu. I spent 1 hour and I completely messed up your head by saying something which eventually I summarized it in one line. Vectors are associated with directional derivatives. Directional derivatives are just a generalization of partial derivatives to any arbitrary direction. That is all. Everything else was just proof of that. Okay? That's all. Now, typically, in vectors, we know that we don't often write the basis. Right? We don't really need that. So this equation here is basically just what we call this transformation law of the vector. It's really components of the vector. And of course, this is of the contravariant vector. This is the transformation law. Law of a contravariant vector. So essentially, any object whose components transform like that, when the coordinates transform from d mu to d mu prime, is called a contravariant vector, or vector for sure. This is a definition of a vector. The same thing that I'm basically repeating the same steps we did in special relativity. Now I'm generalizing. It's not that any object whose components transform like that under Lorentz transformation, because Lorentz transformation is just one particular example of coordinate transformation. Any object whose components transform like that, when the basis changes like that, is called a vector or contravariant vector. Okay. So again, vectors are directional derivatives. And again, obviously, it's the same thing that we did with Lorentz transformation, only it's more general. So that. This is arbitrary and Lorentz transformation linear. I did not ask linearity here, just say any arbitrary transformation. Okay, have that in mind. We could. Okay, if we get that, the rest is pretty much straightforward. So what will be transformation law of covariant vectors? What will be for transformation law? What will be the definition of the covariant vectors? What did we say about covariant vectors?
They act on contravariant vector.
They belong to the cotangent space. They belong to TP star, right? So we looked at them as a set of linear mapping from TP to R. So the classical example, of course, is the gradient. Gradient of f, which we call EF. Apologies. What's the action of the gradient df on a vector?
Divergence.
What?
Divergence.
No. Exactly what you'd expect. So just df below. Nothing else it can be. This is the directional derivative of the function. Look, I'm spending a lot of time on saying things which are very subtle. I just save you with all this headache and say, okay, this is what it is. Why am I doing it like that? There is one crucial point which is really important. I insist on that vectors belong to a point. Same covectors, they belong to a point. We will need to take derivatives of vectors. When we take derivatives of vectors, meaning we have to look at different sets of vectors at two different points. So we have a problem, we cannot do it right away, right? But we need to know which points to take, so we need these directions first, which is what we're doing here, basically, putting back the notion of direction. Okay? Because if now we're saying a vector is a directional derivative, meaning I know which direction the vector is heading. It still belongs to the point, but now I know which direction it's going. Okay? Same thing with the gradient. The gradient belongs to the point. It's a gradient at that point. That's why I use df rather than f. Okay? I have to digest it a little bit. df exists only at the point it is so the same as we use the partial derivative as a natural basis for the vectors, we will use the gradients as a natural basis for the covectors. So the gradients of the coordinate function x mu provide a natural basis to the cotangent space. So remember we had this theta mu e mu is delta mu. So now we have exactly the same thing. Gradient dx mu, which operates on d nu. Nothing but dx mu over dx mu, which is just delta mu. So dx mu basis of dp star, and that means that every object omega I can write as omega mu dx mu. And of course the transformation law of the dual vectors. Transformation law of the dual vectors. Dx mu prime you know how it goes. There's only one thing you should do, which is a what?
Do x nu lambda x eta.
And the components omega nu prime
dou x nu over dou x mu prime omega.
There's nothing else. So this is transformation law of covariant vectors. Covariant vector omega. It's also known as one form. If you want, I can give a theory of P forms, but let's leave it. What about tensors? The rest should be pretty much straightforward. What do we do with tensors? And if I have a KL tensor, then there's nothing much I can do. T nu 1 nu k nu 1 nu l, and then the basis d mu 1, then there is external derivative d mu 2, d mu k, d mu 1, d mu l. This symbol, I don't know if you've seen it before, it's called external derivative. Yeah? Simply means I treat each one independently.
Certain quantum mechanics.
What?
With certain quantum
It's also known as the outer product.
yes.
What?
This is the name.
Yeah, it's outer product, the tensor product. Okay, we've seen that before.
Yes.
Coordinate transformation. T mu1 prime, mu k prime, mu1 prime, mu l prime. What do we do?
From each one of them separate.
Yeah, there's nothing really you can do, right? So we have dx mu1 prime over dx mu1, dx mu2 prime over dx mu2, dx mu k prime over dx mu k, then dx mu1 over dx mu1 prime, dx mu l over dx mu l prime, times t mu1 mu k mu1 mu. Long but straightforward. So this is transformation law of tensors. Okay, let's do an example and then go home. I mean, any example I'll give will be trivial because these are things that you did already. Right? So let's consider an S02 tensor example. Right? So consider 02 tensor we call S on a two-dimensional manifold. Space, and coordinate of the manifold would be x1 is x, x2 is y. And let's take S mu nu, whichever, x, 0, 0, 1. Or I can write it as S is S mu nu, dx mu, dx mu. So how do you write it? You want help me?
X plus
X dx
plus
dy
squared plus
dy.
dy squared. Right. Now let's change the coordinate. So I chose x prime, is x to the 1/3. Prime is e to the power x plus 1. So we can express the old basis, dx mu, in terms of the new basis, dx mu prime. So x is x prime cube. Y is ln of y prime minus x prime cube. Dx is 3x prime squared dx prime. Dy is 1 over y prime, dy prime, minus 3x prime squared dx prime. So basically what is left is to take that and plug it directly in here. Then we end up with S is is 9 x prime to the 4 times 1 plus x prime cubed dx prime squared minus 3 x prime squared over y prime dx prime dy prime plus dy prime dx prime. Note that I made a discrimination, x dy and y dx, because they don't have to be the same, plus 1 over y prime squared dy prime squared, and if you write it in the matrix form, it will be as mu prime 9 x prime to the 4 1 plus x prime cubed will be a minus 3 x prime squared over y prime minus 3 x prime squared over y prime and 1 over y prime squared. This is symmetric. Pretty much that's it. Okay. So today was more mathematical. Maybe this is the most mathematical lecture in the entire semester. Maybe not, I'm not sure. Which essentially, I spent 1.5 hours basically making one sentence, right? Which is vectorial directional derivative. And the reason is I need that to get back the notion of direction while using things that are completely intrinsic to the manifold. So not dependent on the coordinates, not depending on anything. Just having I have a manifold which is specified by the metric. Now I know how to define vectors and tensors, which are external structures which I build on the manifold in an independent way. That was the essence of this lecture. And we end up saying that it's essentially the same thing, right? It's the same transformation laws. There is nothing more sophisticated than what we already had. Pretty much just took what we had from special relativity and generalized, rather than as a basis vectors, the Lorentz transformation, the inverse Lorentz transformation, so on. Now we simply have these components of partial derivatives and gradients as natural coordinate bases. Any questions?
So in the last example, you just showed the line element, right? S.
No, it's not the line element. It's just S is a tensor. It's a 0-2 tensor. It's a 0-2 tensor which is specified. I had initially 2 coordinates, x1 and x2, and I switched to other 2 coordinates. All I wanted to show in this example is what happens to the tensor when I write it in terms of the new coordinates rather than the old coordinates. That's all. Line element is typically used when I write the metric. That may confuse.
It's not a metric?
No, it's not a metric. It's just a general tensor which is specified in any arbitrary manifold. Cool. I use the line element because it helps me to see the metric. Essentially, the metric tells me what is the shortest path between two points on the manifold.
Mm-hmm.
But this is general tensor. It could be anything. This is just a simple example.
And the next question is, who said that we cannot use a coordinate system on curved space?
Oh, we can. Normally. But
yes.
when I define vectors, I don't want to do it in a coordinate dependent way. I will always, what the emphasis here was to show you that vectors and tensors exist on a manifold even without me specifying any coordinates. Okay. Now, practically, I will specify coordinates. Now, you can think of manifolds which you cannot really specify coordinates because you get into you run into troubles. The simple way I can think of is this Mobius strip, right? You know this Mobius strip?
Yes.
Right. This is a non-orientable manifold. And, you can locally set coordinates, but you cannot extend them globally in any way. So, but there are others. Now, in this course, we're not going to run into any. It's just introduction to general relativity. You can envision, you know, more complicated and sophisticated theories, which we might run into that, but this course it's not needed. Right? And again, I skip math because I could easily just draw like 2 hours of math here, and I don't think you will get more physical insight if I were to do that. So hopefully I got you through what I want with the minimum, really the minimum amount of math that's needed to get it through. Okay, the next will be more straightforward. I told you this is sort of half math, half physics, but the emphasis is in physics. Getting there. All right, so see you on Thursday.
רציתי לשאול, קודם בחרנו איזושהי פונקציה מהמניפה מהיריעה למנשים. יש לה פשוט איזשהו